Alright, in this video I'm going to show you how you can analyze any kind of distributed load that can be represented as a function of x simply by taking the area under that function within two bounds a and b, and that area is going to give you the magnitude of the resultant force, which is going to be acting at the centroid of that area. And if we essentially use concepts from elementary mathematics and calculus, where we know that the centroid of an area is given by the integral of x times the function divided by the total area underneath that curve, which is essentially, in our case, just the resultant force, we can obtain an expression for the x coordinate of the centroid. Now, normally, we would actually be finding the centroid of the area in terms of the coordinates x and y. But in this case, because the loading is only along the x-axis, we only care about the x coordinate, so we can just forget about calculating the y coordinate of the centroid. Usually though, when you start looking at a specific section, you would choose a point A as your starting point and a point B as your end point, which are the 2 points within which that continuous function of the distributed load is defined. But normally, if you're looking at the distribution function from the left-hand side, and that's essentially your starting point for the whole structure, then you would simply set A equal to 0. So let's look at how we can actually apply this in a numerical example. Suppose you have a distributed load that has the shape of a square root of x. So basically it looks like this. And then you have a beam of length 6 meters with a hinge support on the left and a roller support on the right hand side. Now the next thing we gotta do is we want to find the resultant force and as well as the location of the resultant force along this beam. So we draw a little area. We know it's gonna look like this. So that's gonna be the area. The resultant force should be somewhere to the right. We know that because from basically just looking at the shape of this, we know that there's more area on this side. So we can already tell that the resultant force is going to be somewhere there. So the first thing we do is we take the resultant force. Now we're gonna use an integral for this. Since this is a very simple structure, we can choose this point over here as our x equals 0. So that's our starting point. And then over here, that's going to be x equals to 6 meters, which is the end of the beam. So that's going to be from 0 to 6. The value of the distributed load is square root of x dx. And now we're going to integrate that. Now remember that you can convert this to a power by simply saying x to the power of half. And by using standard rules of integration, we know that this is going to be x to the power of 3 on 2. Divided by 3 on 2, and we're going to integrate it from 0 to 6. So that becomes 6 to 3 on 2 divided by 3 on 2 minus 0, and then we're going to approximate that in our calculators to 2 decimal places as 9.80 kilonewtons. So that's going to be the magnitude of the resultant force. Now we want to find out the location of the centroid from the left hand side. So we're going to call this x bar. So for x bar, we're going to use the formula above, which is essentially 1 divided by the resultant force. And we're going to take an integral from 0 to 6 once again. But in this case, we're going to multiply the function of the distributed load by x. Okay, so this is essentially like taking a statistical average of all the areas here. That's going to give us the centroid. So the first thing we do is we convert this to a power. So that's going to become 1 over 9.8 of the integral of 0 to 6 over here. And then this is going to be x times x to the power of half, which becomes x to the power of 3 on 2. So let's say we have 1 over 9.8 times x to the power of 5 on 2 divided by 5 on 2. From 0 to 6. So that's 1 over 9.8 times 6 to the power of 5 on 2 over 5 on 2. And if we put that in our calculators, that is going to give us 3.60 kilonewtons. So that means our resultant force is going to be located at 3.6 meters. That should be in meters. Okay, so that's going to be from the left. So now we can draw our free body diagram. as we would normally do. We're going to have a reaction force over here, RA, another one over here, RB. Then at 3.6 meters from the left, we're going to have our resultant force of 9.8 kilonewtons. And then that means that we're going to have a remaining 2.4 meters on this side. Now, there's not going to be any reaction force in the x direction because, once again, we don't have any horizontal external forces. So this is simply going to be that setting. So now we're going to look at this by taking the sum of the forces in the y direction. That's going to be equal to 0. So now the next thing is going to be, okay, so we're going to look at this in terms of forces. So that's going to be minus 9.8 plus RA plus RB. And then RA plus RB is going to be equal to 9.8. And then we take the sum of the moments about A equal to 0. Let's assume this is positive. So the next thing is going to be, we have 3.6 times 9.8. That's going to be in this direction, so that's positive. 3.6 times 9.8. And then we're going to have minus 6 times RB. So RB is going to be equal to, let's see, 3.6 times 9.8 divided by 6. That's going to be 5.88 kilonewtons. And then that means that RA is going to be 9.8 minus this, which is 3.92 kilonewtons. And this makes sense once again because we know that there's more load on the right hand side, so the reaction at B should be higher than the reaction at A. But we notice in this case it's not as obvious as in the case of the triangular load, where we had 1/3, 2/3 and 1/3 respectively. In this case, what we have is there's going to be a different distribution due to the shape of this distributed load. And in the next video, we're going to be applying this concept even further by looking at more composite structures.